Good morning, good afternoon, good evening, everyone. Welcome to the Eliis Technical Forum. We are delighted to have you on board today. I'm Emmanuel Bodia, I'm Product Marketing Manager, and I will be your host for today. We have set up a very interesting and exciting program for you today, and I hope you will enjoy it as much as we do. But before starting or diving on the presentations, I'd like to say a few words about the Livestream platform. That's the platform we are using today for this event, and also about the agenda of today. So first of all, this session will be recorded. So if you need the link to the recording at the end of the event, please reach out and we'll be happy to send it to you. We will not be able to send all the presentation to you, but at least the Eliis presentation, we can share that with you. If you look on your right-hand side, you can see that you have this chat box, and that's where you can put any comments you want. You can put a request or issues, and we will be happy to help. If you look at the bottom part of the chat box, you see that you have the questions tab. So I encourage you to put your questions through this tab, as we will have a 5-minute Q&A session after each presentations. So please use this tab to post your question, and you'll see that on the left-hand side of your question, there is a vote option, so you can vote for the questions. So I also encourage you to vote for the questions you are interested in, so that we can prioritize the questions when it's Q&A session time. Okay, so now let's have a look at the agenda for today. Okay. So the session will be split into two parts. The first part is dedicated to Eliis and partners presentations. And then we have a 5-minute break. And afterwards, we have 2 case studies presentations. So on the first part, we'll start with a short introduction with Marion Barret, our project manager. And she will talk about what happened in 2022 for Eliis, and also the main highlights of the PaleoScan 2022. After that, Julian Chenin from Bluware and Jean-Philippe Adam from Eliis will present the Bluware FAST technology embedded into PaleoScan. And then the last presentation of the first part will be about an integrated seismic interpretation to structural framework workflow. So that would be this new structural framework workflow will be combining both Petrol and PaleoScan technologies, and it will be presented by Benjamin Duro from Eliis and Matthew Elwood from Schlumberger. After the break, we'll have 2 very nice presentations, one from Sumit Verma from UTPB. He will be presenting the evolution of the Permian Basin. And then the second case study will be given by Konstantina Tsikalaki from the Royal Holloway of London. And she will present seismic geomorphology of Upper Cretaceous Cenozoic plays offshore Denmark. So with that, I wish you a very good session and enjoy. Welcome, everyone. I'm pleased to welcome you to this 2022 Technical Forum. So before to start, I want to share with you a few words about this year because it has been intense and very rich for Eliis. So first of all, the Eliis team is getting bigger and bigger. We have a new office in Middle East, in Dubai. You can see that most of our subsidiaries has grown a lot, and you can see that we have new resellers around the world. And this is fundamental because it enables us to build a closer relationship with our customers and so with you. In 2022, it's also a year during which we have done a lot of exciting collaboration.
And this is mainly because at Eliis, we believe that to tackle the huge energy challenges we are facing, the best-in-class applications need to be combined and interact to enable transformational workflows. So that's why we are working closely with other software vendors to facilitate interaction in between our, cutting-edge technologies. So we've done some work with Iron Logics, with Petrol, but also with FAST, a technology from Bluware. And the two last workflows, so the structural framework workflow and the integration of FAST will be presented in the first part of this technical forum. We have also started inspiring collaboration with 45.8 and strengthen the relation we have with Explo Crowd because we want to push forward our technology, PaleoScan, to contribute and accelerate the helium and natural hydrogen exploration, but also virgin reservoirs identification for CO2 storage. Our ambition is still the same, so we want to be the reference in seismic interpretation. And to achieve this goal, we are driven by key strategical themes, and I'm going to present you the three main ones. The first one is related to the fact that the energy industry's success depends on its ability to unlock the enormous digital opportunity offered by the data. And the OSDU data platform is a great example of how collectively an open source standard-based data platform can be built. And so an application such as a PaleoScan needs to adapt to this new data-centric era to fulfill all of these new requirements about standardization and cloud requirements. So Jean-Philippe and Julien will present you in a minute the first step in our OSDU VDS journey for PaleoScan. We are also highly working on how to integrate 1D, 2D, and 3D data to build a comprehensive and detailed geological interpretation. And these themes triggered work on our 2D workflow, on the well data, but also on functionalities that that enable you to do some fine-scale reservoir interpretation. And addressing these challenges are really crucial, in particular because we want to provide our application in more and more CCS projects. So finally, the last themes I want to present is that we continue our efforts on user experience and how to bring closer to our customers the guidance and all the knowledge we have accumulated internally, all our small tip and tricks, workflows, how to bring this and share it with you so as you can become experts tomorrow. So for this release in 2022, our efforts were focused on the two main ones, and I'm just going to present the main highlights of that release. So the first one is the integration of the adaptive streaming fast technology inside the platform, and that would allow you to stream volume that are stored in VDS format in the OSU data platform directly from the application. And that's avoid any import step and you don't duplicate the initial data. To foster the collaboration and the exchange with our key clients, we will provide that functionality as a beta functionality for free in the core application until January 2023. And the aim is to start building the next step together about, our OSDU and VDS journey. We have also done some work on how to boost the performance of the 2D workflow and enhance the user experience. The last key point is that we will be releasing in the coming weeks a new byproduct, a PS data loader. This is mainly for data management tool. It's a smaller PaleoScan where you can import, preview, quality check your data, and export as well all the objects you have imported or generated outcomes. So that should be available soon. And if you're interested, don't hesitate to contact your key sales contact at Eliis. We will be able to provide you some evaluation to test it. So I think that's it for the brief introduction. I think it's time to start the technical forum. And I give the floor to Jean-Philippe and Julien. Enjoy. Thank you very much.
Thank you, Marion. I'm very happy to present the first presentation for this session. First, Good morning, good afternoon, and good evening, everybody. I'm Jean-Philippe Adam. I'm sales manager for Eliis for Europe and Africa, and I'm very glad to have Julian with me from Bluware to present the OSDU journey of PaleoScan using FAST. I will start, let Julian introduce himself, and then we will start the presentation.
Thank you, Jean-Philippe, and good afternoon, good morning, good evening, everyone. Big thank you to Eliis. I'd like to thank them for having us today and letting us participate, as well as for the great collaboration that we've had over the years. My name is Julian Chenin. I'm a geophysical data scientist here at Bluware, and I'm working on both the product and the R&D teams.
Okay, thanks. I will start to share my screen. And yeah. Okay, I will start with a short introduction of OSDU and Eliis, and then I will let Julian introduce VDS and FAST technology, and then we will switch to a live demo of the embedded FAST solution. This presentation is about the phase one of our OSDU journey, how to connect PaleoScan to OSDU environment to liberate data and and how to use the FAST technology to directly stream volume from OSDU. I will start just with a short introduction about the OSDU data platform. Eliis is member of the forum since 2020, and as Marion explained, the main objective of OSDU is to disconnect data from application to unlock the workflow and to have more collaboration between different applications. In the spirit of the openness of OSDU, OpenVDS is now recognized as an exchange format for the Seismic, and due to this and other points, Eliis and Bluware are starting very strong relationship and strategic collaboration to accelerate our main subject, the seismic interpretation time cycle. I will just switch to VDS format, and I will let Julian explain you more about this technology and the FAST technology also.
Yeah, thank you, Jean-Philippe. So yeah, building off of that, as we know, the industry, seismic data has been stored in many formats, whether it be SegD or SegY or even proprietary formats. And so over the last 15 years, Bluware has developed what we call volume data store, or aka VDS, as a modern, efficient, but more importantly, a cloud native format. And so we opened it to the OSDU through the open VDS APIs. So VDS, it's a bricked format, and it enables rapid access to any part of the volume, for example, the inline, crossline, time slice, as well as subvolumes and random 2D tiles. VDS also supports multiple levels of detail, which improves performance in visualization workflows. And this will be key, especially for the different interpretation applications. And then finally, VDS supports dimensions with an unlimited number of auxiliary channels. And so what we mean by that, it supports formats such as like 2D and 3D stacks, gathers, and also it can go towards higher dimension objects. And one of the key features that VDS supports is wavelet compression as well as adaptive streaming, which we will discuss in the next slides. So really, the adaptive compression, when applied to seismic data, this is a critical characteristic of VDS, and this kind of enables a smarter way to access and use seismic data. And so here we see different compression levels or tolerances for different workflows. We start on the left side, which is the legacy format. So this would be, for instance, in SegY, and we have 100% because that's effectively 100% of that legacy format. Bluware has developed true lossless. So there is no loss in data, and we truly mean that, right, in every sense. And so immediately you can go from 100% of the data and compress it by about 25%. And so the use of this is that one, it's cloud native, right, using the VDS format, but also in this instance, you can use it as sort of an archive to preserve it. And from that, you can then derive more aggressive compression, such as perhaps virtually lossless, or you can even introduce some loss depending on the workflow that you're going for. We recommend virtually lossless when you want to do things such as seismic processing, AVO work, and so on, because that is the most sort of numerically stable in terms of the compression, right? If you want to do something that's more regional structural interpretation work or more like basin wide, perhaps you could go with something as some loss, right? Where now you're only at 5% of the data compared to the initial 100%. So you have various different levels of compression depending on the format that you'd like to use, but also you're significantly reducing the data in its size. Next slide, please. And so the way that we like to talk about FAST is kind of the Netflix for your seismic data. What you can do with FAST is really stream these various data on demand through different interpretation platforms. So it makes it readily available for you. In terms of what a seismic interpretation data workflow would typically look like is that geoscientists will usually start with a post-stack survey, which could be anywhere from a few to several hundred gigabytes. For interpretation, this data needs to be converted to various different application formats, right? Such as for the PaleoScan format. And typically this can add a few hundred gigabytes before the interpretation begins. Furthermore, some applications require volume optimization. This can introduce another 400 gigs of data, and many of these applications also perform more efficiently if you break things down into sub-volumes. And so after all of this duplication, right, the data has exponentially grown in size from 200 gigabytes to now an astonishing 2.4 terabytes. And FAST eliminates this by streaming the data, like Netflix, the data into the applications. And all data is created from a single source. It's not copied or duplicated. Rather, it's simply streamed when you need it. And for data managers, this reduces a lot of data management challenges. Taking a typical sort of a look at a typical FAST workflow, our single source of data is stored as a centralized library. And the data from FAST is delivered to applications only as needed. So each application could require its own formats or performance optimizations, right? But all of this information is presented as a virtual folder on the operating system. And so the application, right, the interpretation application then reads data from those virtual files just as if they were saved on a local disk. And so this means that the application, right, does not need to change to consume data in and from the cloud, like with PaleoScan. Looking at the user experience for geoscientists, right, this is a great thing because the end user environment still looks the same on their workstation, as Jean-Philippe will demonstrate in the live demo.
Thanks, Julian. I will cover now the PaleoScan implementation of the FAST technology embedded into FAST. It's part of the new release of PaleoScan 2022. This is the phase one of our journey to OSDU. We are connected on OSDU data platform thanks to the FAST technology. We stream directly VDS format from OSDU and we connect into PaleoScan. And then when we follow the workflow, we compute attributes, volume, model grid, etc. Everything is still stored locally. We just stream the data input, the SegWi, directly into PaleoScan thanks to the adaptive streaming with FAST. Concerning the cloud provider, it's possible to use two different cloud providers with this first release of the embedded FAST solution, AWS and Azure. Just a short example of the comparison between both workflows, the normal one with the import and the one with the FAST, embedded FAST technology. Okay, from a SegWi, a 62 gigs SegWi, we import into PaleoScan format. And then due to the SegWi geometry, we have some area without data, and we have a volume of 81 gigs. And then, as Julian explained, in fact, with PaleoScan, we have to create some optimized file for the fast navigation in inline, cross-line, and time-slice direction. Due to this, we create an inline, a cross-line and time-slice volume, and we double the size of the initial volume. Okay, we add 162 gigs. And then we start, this is just for navigation, and then we start the interpretation workflow with PaleoScan, we create a model grid. To create this model grid and to help the automatic propagation, we smooth a little bit the volume to help the automatic propagation to have better propagation. And we add 82 gigs more. And then we have to store also the grid with all the connection with the automatic propagation. It's 10 gigs more. And at the end, after the automatic propagation and the refinement, we have the final relative geological time model. And if we want to display in inline and crossline direction, we need both direction. It's 162 gigs. And then you can start really the job of interpreter to look at horizon stack, maybe to start sequence stratigraphy. But you arrive to 549 gigs with the traditional and the import-based workflow. Now, if we use VDS and adaptive stream workflow with FAST, in fact, all the first part can be streamed directly. In fact, thanks to the connection to OSU, you can directly stream the VDS format. And then with the VDS format, in fact, all the direction, because it's a block format, as Julian explained, no need to compute the optimized file for crossline and time slice. And due to this, all this phase of visualization, it's a streaming option. It's 0 gigs for all these parts. And then, as I explained, all the output of PaleoScan will be stored locally. We still have currently the model grid, the conditioning, the model grid, the relative geological time model. But just with this workflow, in fact, without compression, with the true lossless option, we arrive to a volume of 318 gigs. And if we use the virtual lossless, the one you can use for AVO or for interpretation, we have less than 300, we have 290 gigs with the initial compression. As you can see, just with the streaming option, okay, we reduce the size of the project by more than 50%. Just especially if you work in exploration with very huge volume, very large data set, 50% of the project size, it can be very important also in terms of cost. As you can see, we just start with a volume of 52 gigs and we win more than, around 200, more than 200 gigs of volume. It's really important. Just before to switch to a live demo, this phase one, it's reduce drastically the time for data management and data transfer. Okay, all the data are centralized on the OSU data platform, and then because it's stream, it's adaptive streaming option, no need to import. Okay, if you have very huge volume, you can spend hours or maybe one day or for the import. You skip totally the import, and all the inline, crossline, and time slice direction are already computed. And we increase a lot the interoperability between all the applications, okay? Because PaleoScan is connected to OSU with FAST, but as Julian explained, we can connect different applications, and like this, you avoid to duplicate the input for all the applications. Also, we have more flexibility to store because VDS, it's a cloud-based object format, and the most important point, we reduce the size of the project and of course the cloud. Okay, if you use OSU, you store all your volume on the cloud. All the storage can be expensive. Thanks to this reduction of the volume, you can really drastically reduce the cost of the storage with the cloud. I will just switch for a video on live demo. Okay, I will use Australian dataset. I already import a PaleoScan format for this one. I will just open and navigate through my volume just to show you the normal navigation with a PaleoScan format. We import the segue as normal one. I import prior to the demonstration. Now we have a new option, the OSU Data Connector. I just need to click, and then I will have directly into PaleoScan a preview. I can choose my cloud provider, Amazon or Azure. I just need to connect, and then I can type the name of the file or click on search to find all the VDS available on my OSU data platform. And then I just have to mount one volume. I have all the information of this volume on OSDU. I can mount. I just have to type a name. Okay, I will use this one. It's true lossless with no compression. I can choose inline, crossline, and time slice selection just to import a part. And PaleoScan will mount. I have a little Bluware icon to say, okay, it's VDS and stream volume. I will do exactly the same with virtual lossless just to compare the two volume with true lossless and virtual lossless. Okay, this one it's virtual lossless. And then just to show you the navigation, I will open my two objects. The first one with the true lossless. Okay, as you can see, I can navigate through inline direction exactly as my PaleoScan format. I will do exactly the same with the virtual lossless. Of course, we compress a lot the size of the project, but the navigation is still the same, and we will compare the quality of the data just after during the presentation. Okay, now I just reorganize my PaleoScan. I will open the three different volumes just to compare, just organize my windows. Okay, as all the object of PaleoScan, of course, first thing I can do, I will show you on the PaleoScan object, I can change my color bar, I can change the color distribution, the limit. Okay, I can really adjust all the parameters to find the best color bar as possible for the display. And because my VDS stream volume are exactly as any volume of PaleoScan, I can drag and drop to have exactly the same color bar as my PaleoScan format. And then I will just zoom in just to show you the quality of the data between PaleoScan, the true lossless, and the virtual lossless. Okay, the most important is the two section on the right between the true lossless and the virtual lossless. As you can see, I have the same level of detail to use PaleoScan to interpret. Okay, we don't have loss in terms of interpretation. We can directly use the virtual lossless as input for the model grid, for all the interpretation stuff. And of course, we will reduce drastically the size of the storage using the virtual lossless volume. Then, as all the object of PaleoScan, I have access to the property. I just have to click inside. And for the volume, I have access to the real-time attribute. Okay, I will start with the PaleoScan format. I can compute some real-time attribute, for example, as RMS amplitude. I will compute my RMS amplitude. I can still navigate, and PaleoScan will compute in real-time the RMS amplitude. Now, let's try with stream volume. Just choose RMS amplitude. I can still navigate. Just to show you, I can change also the vertical windows for the computation. And as all the volume of PaleoScan, I can compute this real-time attribute. Exactly the same with the virtual lossless. I will start with the RMS amplitude. Okay, it's exactly the same display. I can navigate. I can switch to other attributes, for example, sweetness or seismic relief, and PaleoScan will compute on the fly. Now, if I want to compute the crossline for my PaleoScan project, okay, and display the crossline, I just have to click, and then normally I have to compute. It's why I have a red dot. Now with stream option, it's already available due to the format of the VDS, and I just have to switch, and no need to compute the crossline. PaleoScan will display also with the real-time attribute, exactly the same with the seismic relief, and I can navigate, and I will have the same navigation in crossline direction. Okay, now exactly the same as time slice. I will just remove my virtual attribute, my real-time attribute, because it's compute only on frame. I just have to click on it and then display the time slice. And PaleoScan, due to the format of VDS and the streaming option, I can display directly, without any computation, without any storage, my time slice in both true lossless and virtual lossless. Okay, yes, I can change again my color bar just to show you. I can drag and drop from the true lossless to the virtual lossless. Just to finalize this live demo, just to show you it's exactly as any volume of PaleoScan, even if it's a stream volume, I will start the beginning of the seismic interpretation workflow with PaleoScan. I will compute my model grid. Okay, I will just close my windows and I will compute a new 3D model grid. And as you can see, as the input of the volume, I have access to my stream volume, okay, the true lossless and the vertical lossless. I can choose any volume. I will use the true lossless. I can choose my parameter, patch size, polarity for the vertical resolution. I can, of course, use all the advanced options, for example, reduce just between two horizons in case, for example, of more precise interpretation. And then PaleoScan will compute my model grid with my automatic propagation, okay? And then I can start my workflow. I will just stop on this part and come back to my presentation. Okay. Just as conclusion, during this presentation and live demo, I'll show you the part one of our phase one, as our OSU journey. Now PaleoScan is connected to OSU data platform thanks to the fast and thanks to the adaptive streaming. But everything is stored locally. All the output of PaleoScan are still on the local store. The next step will be the ingestion phase. That means all the output of PaleoScan, for example, the relative geological time model, to be able to export, for example, as VDS format and re-inject into OSU data platform. And like this, we will have the import and the output. Like this, other software can consume directly the output of the PaleoScan workflow from the OSU data platform. Thank you for your attention. I was very happy to present you this new feature with Julian, and don't hesitate if you have any question about this new workflow with PaleoScan.
Thank you very much, Jean-Philippe and Julian, for this very instructive presentation. It was very much appreciated. So please post your questions if you have questions in the chat or in the questions tab, so that Jean-Philippe and Julian can answer the questions. But in the meantime, I have a question for you. How long does it take to access a VDS in PaleoScan? Who wants to answer that?
Julian, with the fast, because it's
Sure. Yeah, and actually, having used this myself, it's almost immediate. I mean, it's essentially the same as if it were a local file. When you access it through fast, it's the same performance. And so again, the geoscience experience using PaleoScan still remains the same. So it's still a very familiar environment to them. Jean-Philippe, did you want to add as well?
No, it's perfect. I tried different workflow. It's depending the size of your and the number of volume you have on your OSU data platform. If you have many volume, it's just the search option. Maybe it's just the time to find all the VDS. But as soon as you mount the volume, it's almost immediate access to the data.
Pretty impressive.
Completely, you skip completely the import phase of PaleoScan.
Okay, great, thank you. I have another question for you. Does embedded fast features work only with VDS files stored in OSDU?
Yeah, the fast technology work not only with VDS on OSU, but the implementation of embedded fast into PaleoScan, it's currently only for OSU data platform. We will see in the future if we implement direct connection with VDS store on local machine, on private cloud, or this kind of thing. But for the embedded fast solution, yes, for the fast solution and other application, it's possible to stream VDS not only from OSU.
Thank you, Jean-Philippe. We've got a question on the question box. So we create VDS in a cloud and then stream it to our network. It is great that the volume is smaller, but what is the primary constraint to performance? Is it bandwidth or memory? Julian, do you want to take that one?
Sure. Yeah, and that's a great question, Brian. So we've actually done different testing, whether we have, say, that file through VDS and the same one stored locally on an SSD, different types of formats to sort of compare how they perform. Really, the primary one is based off of the levels of detail, right? That's the primary constraint, and also in terms of like the numerical stability. So if you're very aggressive kind of with the compression, it'll be slightly better in terms of performance. Virtually lossless still performs almost as well. So really it comes down to level of detail.
Okay, great. Thank you very much, Julian. Okay, I think we are ready to move on. It's the next presentation will be about the Schlumberger and Eliis integrated seismic interpretation to structural framework workflow. So I'd like to call Benjamin and Matthew to present their work on that.
Thank you, Emmanuel. So thank you, Julian and Jean-Philippe for the great presentation. So my name is Benjamin Giraud. I'm a geologist by background. And actually, Schlumberger and Eliis have been collaborating for the past few months on behalf of a common clients on this topic. So how we can integrate the seismic interpretation to a structural framework workflow. So I will just leave the floor to Matthew so he can introduce himself, and he will start talking about this presentation.
Great, thanks Ben, and hello everyone. My name is Matthew Elwood, and I'm a geologist at Schlumberger, and I look after some of the structural modeling technology we have inside Petrol. And as Benjamin says, today really we're looking at a workflow as to how we can better connect the PaleoScan and Petrol platforms to, well, that was really inspired by one of our customers to really improve the connection between interpretation in PaleoScan and the creation of subsurface models in Petrol. So we're going to take you through a workflow, we're going to give you a demo, and then we'll have some time for questions at the end. But I think it's important to start by discussing what the challenge is and why we worked on this problem together. I think everyone who's involved in building subsurface models knows that as geoscientists we face quite a broad range of issues that impede our efficiency in generating those models. And in particular, when operating between multiple software platforms, it can be quite difficult to transfer data and maintain its fidelity through that transfer process. But it's also the case that when we collaborate with different subsurface team members to build that reservoir model, we can end up with disconnections between the various interpretation stages, which results in a lot of inconsistencies. And when we get to the time to build that subsurface model, it can be quite painstaking to reconcile those differences and use those or massage those inputs to produce a final robust reservoir model. So ultimately, the impact of this is that the timelines to produce the subsurface models are really extended far longer than they necessarily need to be. And the quality of models are impacted. So we're making poorer quality decisions because we have incomplete or inconsistent models in certain places, and we have long cycle times to produce those model outcomes. So what we're looking at is how we can drive more efficiency and higher quality subsurface models through better collaboration. So in terms of the integrated workflow, what does that actually mean? As I just described, it's really about accelerating the interpretation to framework process, and we do that through updates to the connector. So the connector provides an ability to transfer data between Petrol and PaleoScan. So additional support has been added to that connector to enable the transfer of triangle meshes, which are a great way to represent our fault geometries. And then a new process has been added to Petrol that enables us to take the outputs from PaleoScan, in this case in the form of an RGT seismic volume, and use that to update our structural model. And this is quite beneficial because it allows us to have a common stratigraphic reference in the form of a well with associated well tops in Petrol, and over a number of iterations, when we generate the RGT outputs, extract new horizons and incorporate them in our subsurface model. And you'll see that in the demonstration a bit later today. So as a workflow, we really sort of start the workflow by generating our core structural interpretations in the form of our fault network. So we use the fault framework process in Petrol to generate a series of fault surfaces, fault model elements that have various interactions between the other faults where they truncate against each other. And this is produced by taking fault interpretations in Petrol through machine learning or through traditional interpretation workflows, inserting them in the fault framework process, and then generating a fault model. We can then interpret horizons using various techniques in Petrol or elsewhere to represent sort of the main stratigraphic sequences of our model, and we can use those to refine and constrain the relative geologic time process, the model grid creation, and Ben's going to show that. It's an optional step in the workflow, but it does improve the efficiency of the overall workflow. And once we've generated those outputs, we can take those via the connector into PaleoScan, produce our relative geologic time and constrain it to these structural interpretations. Produce this higher resolution, refined interpretation of our core sequences, and then take that back into Petrol and use it to drive updates in our structural model. So let's take a look first now at where the modeling workflow begins. So essentially we start, as I said, by generating our fault interpretations and passing those into the fault framework process. And then we complement that with the option to generate our horizons and consume those then in PaleoScan. So we're going to walk through that aspect of the workflow inside Petrol. So here you can see I've got a project in Petrol. Within that project, I've got a series of fault interpretations, and those fault interpretations I can then drop in the structural framework process to produce a fault framework. And you can see the outcome of that process here and the connection of those different faults between each other that I can then modify and work to optimize, and then use as a reference to then interpret my horizons to then start to build up my stratigraphic understanding. Once I've interpreted those horizons, I can drop them into the structural framework process in Petrol to build out my major sequences. So in this case, we've got a large regional unconformity and then 2 conformable horizons. And you can see now the outputs that were generated by the structural framework process that produces our structural framework model. And if you look at the sequences, you can also see in blue, there's a conformable sequence here, which we're going to then refine using the RGT workflow in PaleoScan to add additional resolution that's seismic and structurally consistent to improve my reservoir characterization. So to continue that workflow in PaleoScan, I need to be able to transfer that data. So I'm going to use the connector to share that information from my Petrol project into my PaleoScan project. And I can simply do that by right-clicking on the fault framework, converting that fault framework to triangle meshes, which creates new objects in the input tree. And I can use a short workflow, or I can use my existing horizon interpretations to generate bounding surfaces that I then use in the generation of the model grid. And Ben's going to walk you through that process. But of course, to send them across, I need to open the connector, select the objects that I would like to transfer. In this case, I'm sending the surfaces, some key interpretations, and I'm also identifying my folder with all of my triangle meshes for my faults and adding them into the connector and sending them across to my PaleoScan project. So once I've done that, I've prepared everything for Ben, and Ben can take over and continue the workflow in PaleoScan to produce the structure constrained relative geologic time model. So Ben, over to you.
Yeah, thank you, Matthew. So now everything has been transferred from Petrol to PaleoScan. So if you just move on to the next slide, Matthew, please. Then all the data is now in PaleoScan. So it has been successfully transferred. That's perfect. And now, Matthew, yeah. So actually now, because it is 3D data, so the idea will be to create a model grid. Okay, so I will click on the first icon to open the interface. So I will just click on the seismic because I want to use this one, and of course because we don't want to create the grid on the entire data that is just to work on a specific stratigraphic interval. So I'm going to bound the grid using 2 horizons that we have previously interpreted within Petrol. So as is in the horizon one, I will just use the top surface, and in the second one, I will use the base surface. So now, actually, to better constrain and consider the seismic events we're going to use to bounce the grid, the idea is to shift them up and down. So I will just type minus 100 meters to shift the upper limit upward. Okay, and I will just repeat the operation for the lower limit. This time I will just type plus 100 meters just to shift the lower limits downwards. So now the idea is just to go back in the grid parameters. So I'm gonna put the seeds in the middle of the data. And in here, because the data is not really continuous, I will just reduce the patch size down to 3 to have a better propagation. And I will just also leave the polarity as it is. Because we have some faults, it is important to include them in the grid. So I will just drop them in, and I will also drop them in a seismic view so we can just take a look at them. Once I have set all the parameters, the next step is to click on test parameters. And of course, PaleoScan will create a small grid around the seed so I can just take a look at it. And PaleoScan will also consider the fault. So it is important to the fault because it will stop the propagation. Okay, so it will prevent PaleoScan from making any wrong mistakes. So the Geomodel looks good. Then we display the grid. The grid is bounded between the two surfaces. So far, everything looks quite okay. PaleoScan takes into account everything I have set. So we can click on save. PaleoScan will, of course, summarize all the parameters we have used. And then we can click on run. So PaleoScan is going to create the grid, the model grid. So once the model grid has been created, actually, so 2 files are going to be generated. So sorry, Matthew, it is the next video. Yeah. Thank you. Yeah. So now the two now the model grid has been created. Well, sorry, themes, we have an issue. Yeah, it's so now the grid has been created. So we have 2 files, okay, created in the data, in the tree. So we have the initial grids and the automatic interpretation. So we have to start from the automatic interpretation because this is where PaleoScan has generated all the horizons. And PaleoScan is going to open 2 windows. So I'll just tie them up. So in the upper window, we can see the cross section. So this is just the seismic inline. And in the lower window, we can see the map view. So now my task is just to QC what PaleoScan did. So I'm just going to digitize all the horizons, and you can see because of the faults, the propagation is quite limited, and this will prevent PaleoScan from making any mistake. Okay, so now I'm just connecting all the patches altogether because they belong to the same seismic event. Okay, and so once the horizon is complete from wall to wall in the survey, then we can click on M to validate and mark the horizons. Once this has been done, of course, we can just move on to another seismic event. So this is what I'm currently doing now. So I will just keep connecting all the pieces. So I go on the western side of the survey. I will just keep adding all the pieces. Then I will just move on to the side. I will just keep editing keep connecting all the pieces. So by just clicking, so you can set, even if we put all of faults, the connection goes fairly quick because we just have to click and PaleoScan will connect all the stratigraphic events all together. So of course, the idea will be to do it over and over. Okay, it all depends on the time that we have ahead of us, of course. So here is all the horizons I have QC'd, so in just a couple of days. So far, they look quite okay to me. So once it's okay, the next step is to create the Geomodel, so the relative geology time model, so the RGT. So because I didn't spend too much time QCing it, I will just increase the interpolation size, okay? So PaleoScan will fill the gaps. And for the same reason, I will just decrease the link probability down to 1. And of course, I will use the fault because I want PaleoScan to consider the faults for this workflow. Once it's okay, I will just click on save. So I can, of course, give a name. I will just leave it as it is. I can click on OK, and so PaleoScan will just run the RGT. And of course, once it is run, I can just send this RGT into Petrol using the plugin. And so now the data is back to Matthew.
Great, perfect. So as Ben just described, I'm going to continue the workflow in Petrol, right? So he's just generated for me a relative geologic time volume, which is refining the sequence of interest, the conformable sequence I showed in the first part of the demonstration. And then I'm going to use a stratigraphic reference, which is a well with some well tops, to define which horizons I plan to extract and the relative order of the different horizons in the structural model. So with that, I can step back into Petrol and just gonna try again. It's going to launch again. Okay, nice. So inside Petrol, I can then find that volume that Ben has just generated. I can then identify the survey within which I want to add that and then import that into Petrol. And once I have that geomodel in Petrol, it acts as a regular seismic object in Petrol. I can control its color tables, its opacity, etc., and set up the view as I need it. And then using the new process called Seismic Stratigraphy, I can right-click on the structural model that I created initially to represent the main sequences. And within that, I can identify the well tops that correspond to existing horizons. And you can see here I've got additional well tops that don't have horizons in the model. So I'm going to extract 4 new horizons from the data and then automatically add them into the structural model and rerun that process. So here you can see I've pressed apply. In the background, that's all run. After that's completed, the outputs that you'll see are these 4 horizon extractions, which are consistent with the fault interpretation, which is important because it means that then we're going to have quite a consistent interpretation at the faults and also between the various horizons in the sequence. So you can see those horizons have now been included in the model, and I can start to QC that model. And actually, as I'm QCing that model, I can identify areas where perhaps there may be some more time needed in terms of the PaleoScan workflow to connect and improve the RGT interpretation. And in this instance, I can use an attribute like fault throw consistency to identify areas where I have fault throw reversals at the horizon fault contacts, and then target those areas for improvement in PaleoScan. So here you can see in the red color, I have a reversal locally along the fault plane, and that's an area that corresponds to some issues in my interpretation in PaleoScan. So this is quite nice because it then gives me that ability to feed that back to Benjamin. I can tell him which seismic line this relates to, and then he can go back and review the interpretation inside PaleoScan, update that and pass that back to me, and I can continue updating the structural model. So Ben's going to then show you the process to update the interpretation in PaleoScan.
Yeah, exactly. So thanks. So now I have this information from Matt. Then actually I know that there is a discrepancy between the 2 data. So actually we can open a Geomodel. Okay. So this is what I'm about to do here. I will just open the Geomodel in a cross section. Okay, so first can open this viewer here. I will just synchronize both viewers, and I can start just panning through the data just to find the discrepancy between the Geomodel and the seismic. So Matthew told me that the issue was in a crossing direction. So I will just flip the seismic line into a cross line view and type 12701, which is the location of the cross line. I will just repeat the operation for the Geomodel, and indeed, when we compare both views, we can see that the Geomodel doesn't really honor the seismic events. So to fix this, the idea is just to go back in the grid. We keep adding some patch and some connections, so you can see the yellow lines. that I'm picking in the cross section in a seismic view. And actually, you can also see them in the Geomodel view. So it is of high interest because you can also have an idea of what will be the impact of the connections I am currently doing. And of course, once we're happy with all the connections we have done, the Geomodel won't be updated on the fly. Okay, so I have to regenerate a new one. So for the sake here of the demo, I will just use the same parameters, so we can just compare both of them. So we use 31 and 1. And of course, I will just name it V2. Okay, so then I will click on OK. And PaleoScan is going to create a new RGT model. So now in the next slide, PaleoScan has generated the second cube. Okay, so I have it stored in the data tree. So I can just open it up. So I do a right click on it. I will just select the open option. I will just enlarge the window. I will zoom in. I will also flip it into a cross line. Okay, I will type 12701. Now both are in the same directions. Then I can just synchronize both viewers. And when I zoom in one viewer, the other will just move along. And I can see that the second version of this RGT now looks much better compared to the seismic. We don't have these sequence variations. It looks more conformable, and it honors better the seismic data. So now, thanks to Matthew, I know where the issue was. I could enhance it, and now I can just send it back into Petrol using the plugin. And this new RGT can be consumed in Petrol.
Okay, perfect. Yeah, thanks, Ben. So as you can see, we've kind of got this nice integration now between interpretation and modeling, where I'm identifying issues, feeding that back to Ben. He can update the interpretation, and then ultimately I can consume it. So to consume the output of what he just generated, of course, I need to reopen the connector. In the connector, I then find the volume that I want to consume. I, again, import it into the relevant survey. Once I've imported that in, then I can use it to update my model. There's a fairly simple way to do that. So here you can see the improvement that makes in terms of the consistency locally. So to update the model, I can just make a very simple copy of the parameters using the replicate functionality. And then within that, I can then change the seismic input in the model, press apply, and I'll rerun the entire model. And of course, that will then process, and then I can compare the output results. In this case, I reran the fault throw consistency attribute, and you can see it's all now in a blue color, which is highlighting that the throw itself is consistent, and you can see the horizon fault contacts are now much more consistent because we updated all of those additional conformable horizons in the sequence by updating the RGT volume. So as you can see through that process, we're really improving the model quality, and we have this quick feedback loop between the actions we're performing in PaleoScan and the updates we see in our structural model in Petrol. So really, that's the workflow from an end-to-end perspective. You can see that we started in Petrol, we generated our fault framework, we generated our horizon interpretations to bound our sequences, we transferred that to PaleoScan, and we use that to produce a structurally constrained relative geologic time volume. And then over the various iterations, we're able to extract information from that relative geologic time and update some of the parts of our structural model to improve the final model for consumption in our reservoir characterization workflows. And once that's finished, or once I've produced the structural framework that I need, I can then drop that into the gridding processes in Petrol to directly create a depot grid, a cut cell grid, representing the full complexity of that structural framework model, or a stair-step grid to also, again, capture the complexity from that structural framework model, and then consume that in reservoir property population and ultimately reservoir simulation. So you can see I can continue my workflow end to end and have that integration from interpretation to model to simulation. So really, as I said at the start of the presentation, we're accelerating the interpretation to framework process through the updates to the connector and the new Petrol process supporting the update of structural frameworks from the relative geologic time volume. And that's really aimed at improving the integration between the PaleoScan and Petrol platforms, producing more consistent structural interpretations to ensure that we produce higher quality structural models, and ultimately reducing the cycle time to produce structural models that then drive decisions. So with that, I think we have some time for questions. So Emmanuel, welcome back.
Yeah. Thank you very much, Ben and Matt, for this great presentation. It's really interesting to see how this workflow can speed up the whole structural modeling process. So thank you for that. Yes, we did get a couple of questions in the questions tab. So the first one is, are you guys working in PSTM or PSDM on a structural model? I don't know who wants to take that one.
Yeah, so actually with this structural model here, we were working in depth, actually. So from a PaleoScan point of view, it doesn't matter if you do work in time or depth, but down the road, I think it is easier to work in depth. I mean, you have to work in depth. So this demonstration here, we have used depth data.
Yeah, I would concur indeed. When we're producing the structural model, it's very beneficial to work in depth if you have a depth volume available to you.
Good, thank you. There is another one. Hi, Matthew. How open can we set fractures, faults to modeling transmissibility, contamination, leakage, etc.?
Yeah, so I guess that's really a continuation of the workflow. So when you saw the structural interpretation and ultimately the complex compartmentalization that produces in my structural model, I can then consume that structural model to create a grid. And at the gridding stage, then I can start to think about the impact of fractures and also the impact of faults in terms of the connectivity between my various faulted compartments. So the depot grid workflow and the stair-step grid workflow have options to compute fault seal analysis properties through SGR and associated fault permeability and thickness, and consume that in the reservoir simulator. And equally, if you want to assess the impact of fractures, then you can generate a fracture network on your grid and consume that in dual porosity, dual permeability simulation. So it really connects through, but of course that's analysis that we do at the gridding stage.
Great, thank you, Matt. I've got a question for Ben. How do I know the model grid is refined enough?
Yeah, so actually we have, with this workflow, I would say that we have two ways of knowing if the geomodel is refined enough. So the first way is in the process of the interpretation. So in PaleoScan, actually I didn't show it in the presentation here, but we have a preview. So when we are in the process of doing the interpretation, we can display a preview before running the real RGT. And this preview will let us know if PaleoScan does a great job or not, or if it does need some help. So this is the first step, using the preview of PaleoScan. Of course, you can run the real RGT, but it will take a bit of time. And with this workflow here, the second tool that we can use is when you use Petrol, when you do this workflow, actually you have the fault through consistency attributes that you can map on the fault plane. And as Matthew showed, actually it gives you a different range of color. So when you have a gap within this color, then it is telling you that there is something wrong with the RGT.
Thank you for this clarification, Ben. Another question, would it be possible to consider structural uncertainties by using this approach? Maybe Matt, maybe.
Yeah, this is something I can address in part. So the structural framework workflow is really based on consuming interpretation data to produce a consistent structural model. So if you want to consider uncertainty, then we need to generate alternative interpretations, and we can do that through using alternate velocity models. We can do depth-to-depth conversion. So there are some different workflows we have available directly in Petrol to produce alternative outputs to then consider structural uncertainty. But really, that's a workflow that requires a bit of involvement, and if you require more details on that, perhaps you can reach out to Schlumberger or myself, and I can help walk you through that process in more detail.
Thank you, Matt. I've got another question for you. Are there options in the seismic stratigraphy process to extract horizons and review them separately before running a model update?
Yep, absolutely. And I think that's something that's important to highlight. Sometimes if we've got a complex model, it may take some time to run the end-to-end process, and we may want to get a first look at the horizons we're extracting from the RGT. So we provide an option in the process just to generate the horizon outputs. You can QC them and you can manually drop them in, or you can go back to the process and automate the update of the structural model. So that is available to users.
Thank you very much. There is another question here. Were surfaces from RGT model extracted automatically if they matched a well top where the surface intersects the well?
Yep, exactly. That's the concept, right?
That's
There's
the concept.
a reference well, and the intersection between the well top and the RGT volume obviously will then generate a value of the RGT volume, and then we extract that ISO value across the RGT volume and then generate horizons based on that.
Great, thank you, Matt. Another question for Ben. Where can I access the Petrol PaleoScan plugin?
Yeah. So actually, so the plugin is developed by Eliis, so you can download it from our website, elisgeo.fr. But actually, so once you have downloaded it, you can install it on your machine. And actually, the plugin will be available from Petrol. Okay, so if you open Petrol, you're going to have access to processes panes. And within these panes, then you will see a tool called PaleoScan Data Connector. So you can just double click on it, and then you can just drag and drop objects in sometimes, and the plugin will just automatically transfer and convert the data from a Petrol format to a PaleoScan format, and it works both ways.
Thank you very much, Ben and Matt, for these very clear presentations and answers to the questions. Then I wish you a very good day or a very good evening, and I hope to see you soon. Goodbye.